Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
Alright, so this is chapter 4. Alright, this is the beginning of chapter 4. And chapter 4 is applications of differentiation. Alright, and in 4.1, we're gonna discuss extrema on an interval. Alright, so let's start first with a definition. And we're gonna start with a couple of definitions before we take a look at some examples. Alright, so the first definition we have here is for what an extrema is. So the extrema of a function. Or I should be saying what they are. So let f be defined on some interval I containing c. Right? If f of c, well, actually, let me rephrase that. F of c is the minimum of f on I, so the minimum of the function of f on I, when f of c is less than or equal to f of x for all x in I. So what is this saying? It's saying here some value is the minimum of the function in an interval when that value is less than or equal to the rest of the function for all x in that interval. All right. Now, the next definition is very similar, so I'm gonna do the following. So f of c is the maximum of f on I when f of c is greater than or equal to f of x for all x in I. Right? So again, what does it say? Some value f of c is the maximum of the function on an interval I when that value is greater than or equal to the rest of the function throughout that interval. All right? So that's what that's saying. In here, these values, the min and the max, so the min and the max values are called extrema. All right? And extrema is the plural form. The singular would be extremum. Extremum would be the singular form. All right. So the minimum and max value are called extrema of the function on the interval. All right. We can also call these absolute or global max. Are also called the absolute max or min. Another way to say that is also global max or min on the interval. Right. In general, the extrema, the max and min, can occur anywhere on the in the interval, right? It can be even at the endpoint. All right. So let's get a theorem. Theorem. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 1 So like I said, I'm going to get a few definitions in, and then we'll take a look at some visuals. The extreme value theorem. All right. And this is what the extreme value theorem says. If f is continuous on a closed interval, AB, then f has both a minimum and a maximum on that interval. All right. So as long as the function is continuous, it will have a minimum or a maximum. And again, we'll take a look at some visuals of that in a little bit. The next thing I want to define here is relative extrema. And relative extrema, well, they are a type of extrema, right? And we already said what extrema were. Remember, those were the max and minimum values. So relative extrema is a kind of that, a type of that extrema. So it would be minimum and max values. If there is an open interval, so if there is an open interval containing C, right, on which f of C is a max, then f of C is called a relative maximum of f, right? So if there's an open interval containing C on which f of C is a max, then f of C is called a relative max of f. We can also say that that f has a relative max at that point, right? The point C f of C. And the next thing, it's going to be a very similar definition, so I'm just going to do the following. If there is an open interval containing C on which f of C is a minimum, then f of C is called a relative min of f. All right. So it's pretty much the same definition, right? And again, we can also say here that the function f has a relative minimum at that point, c comma f of c. All right. So another way of saying relative extrema, you could also say local extrema, by the way. I just want to mention that because, well, they're really saying the same exact thing, and I might be going back and forth between those words throughout the rest of the course. So, all right. So now let's look at some visuals. All right. So first, let's look at this following. So let's say that we have this. Let's say that we have something that look like this, right? And let's talk about all of these points that I have labeled there. All right. So this is in the closed interval from A to B. All right. Now in here, we've got some values here. This right here, it is a minimum. Not only is it a minimum, it's actually a relative and a global or absolute minimum throughout this interval from A to B. This value right here would be a max, a maximum. And this one would only be a global max. All right. Now, how come this cannot be a local max? Well, or a relative max, right? The reason it can't be a relative maximum is that, well, for the relative definition, we needed to have an open interval on which C exists. This value here does not exist on an open interval because there's nothing on the other side of it, right? So it's not an open interval, it would be a closed interval because there's nothing on the other side. So this one, that's why this is only an absolute or a global max, whereas this one is an absolute and a global minimum. This point over here, nothing as far as what we are speaking about here. All right. All right. So now let's look at something very, very similar. In fact, I'm going to go ahead and copy this. All right. So let's shift this over a little bit. There we go. So now in this second scenario, let me change a little bit of this before we talk about it. So the very first thing I'm going to look at here is, well, we're no longer going to look at a closed interval. We're going to look at this as an open interval. And because it's an open interval, well, these points would not be included. Well, so we would have actually open circles there. All right, so in here, there's no max, but there's still going to be a relative and a local, a relative and a global minimum. Hold on. Technical difficulties. All right, here we go. All right. So, yeah, so again, the difference here between this closed interval and this open interval is that, well, in here, there's absolutely no maximum, all right? And that's because, well, in here it's opened. Well, you could say, what about the value right before it? But the value right before it, what is the value right before it? All right, there is no smaller value than that. So think about this. What do I mean by that? If I have the value 5, what's the biggest number less than 5? Well, you could think, well, what about 4? But there's values bigger than 4 less than 5, like 4.9, right? But there's values bigger than that, like 4.99 or 4.999, right? The idea here is that we can continue to get closer to that, and there will be no biggest value less than 5, right? So in here, there's no biggest value less than this point right there. So that's why this would not have a maximum, right? But it does have this minimum, this relative minimum, and it's an absolute minimum as well, right? Next one. So I will copy this again, and let's see the next scenario. All right. And by the way, these same ideas that I'm talking about with the minimums, they would apply to maximums as well, right? Like if it was everything facing upside down, it would be a similar idea. All right, so now let's say that that we have a closed interval again, but now at that point down there, we have an open circle. So in other words, it is not filled in there. All right. So in there, we still have this global max, right? We still have that global max, but we don't have the minimum. And it would neither be a local or a global minimum. All right. There's no smallest value around here, but we do have this biggest value. All right. So this is the biggest value that exists. Similarly, if we look at, hold on. So I just said here there should be no minimum. There we go. No minimum. Neither local nor global. All right. Okay. Now let's look at the next scenario. In here, well, we're gonna make this an open interval, right? And the other thing that we're gonna do here is, well, we're gonna change every single one of these. And every one of those is gonna be an open circle. Alright, so now, in this scenario, well, how does this change? Well, it turns out that in here, there's gonna be neither a max or a minimum. So no max and no minimum. Alright, neither global nor relative. Alright, because again in here there's no biggest value less than there, there's no smallest value less than that spot. Alright, so in there we have none of those. So in here we've seen what global minimums look, global minimums look like, and maxes and things like that. Well, what is the scenario that we're really looking for? The one that we will be studying overall looks more like the following. So something like that. We have here a continuous function throughout all the real numbers, and we have here this point, this point. These are called the relative max and mins. So relative max and relative min. Because near it, right, locally, relative to everything near that, it's the biggest value. Or over here, relative to that, that's the smallest value. All right, so that's what makes it a relative min. And notice there that I put those parentheses on both sides of that because it needed to be on an open interval, right? Open interval, not closed interval. But either way, in here, that's a relative max and a relative min. There are some other ways that a function may look that we will care about. So let's see some of these other scenarios. So for example, what happens around things like an asymptote? All right, so we can have things that look like this, right? Let's bring that down. There we go. So something like that. In here, we've got a relative max, but we don't have a relative min anywhere. All right, there is no absolute min and no absolute max. Right? There's no absolute max or min. There's no absolute max because here this goes down to positive infinity. There's no absolute min because this goes down to negative infinity. This is the relative max, but there's no relative minimums here because there's no point that you can say, well, in there on both sides is the smallest point, right? For example, if I start here to the right, there are smaller values, so that wouldn't be the smallest point anywhere near that, and that continues to happen throughout that entire interval as well as this entire interval. So this will only have a relative max. We can have something like an absolute value function, right? In here, we've got this point right here is both a relative and an absolute minimum. So relative and absolute. It's relative because near it is the smallest value. It's absolute because throughout the entire domain of the function, it is the smallest value. All right. And I mean, there's also there can also be variations and combinations of all these that we just saw here, right? To talk about that, so let's start by first. Well, let's focus on these relative minimums and maximums. All right. Because so the reason we're gonna focus on the relative ones is because, well, the absolute ones require us looking throughout the entire interval. Well, let's not worry about that scenario right now. Let's worry about just how to find the relative minimums and maximums. All right, and we're gonna do that using calculus. So first, let's talk about something called a critical number. So definition. a critical number or critical numbers. All right. Let f be defined at C. If f prime of C is equal to 0, or f prime of C is undefined, then C is a critical number or value of f at the point C comma f of C. All right. I didn't mean to say at. I want to say and the point C comma f of C is a critical point. All right. So what is this saying? Well, we're saying that the function is defined at f. This means the function f is defined at C. There we go. So C is in the domain of f. However, f prime of C is 0 or it's undefined. So that gives us some restrictions as to what's happening with the derivative. All right. And when those restrictions are satisfied, right, then we call that value a critical number or a critical point if you're talking about the actual coordinate. All right. So let's see how this helps here. Well, let's say that we had this scenario, right? In here, this point is at C, and in here, f of C is defined, right? It is defined because it's an actual value up here. So this is f of C at that height, right? However, f prime of C is undefined. Well, how come? Well, f prime, remember that f prime talks about this derivative, right? And slopes. In here, what we have is a cusp, right? We have a corner. And in cusps, it turns out that the function is not differentiable. So because it's not differentiable at the cusps, then f prime of C cannot exist. It's undefined there. All right. So in here, we would say C is a critical number. That's how you spell critical. My spelling's off the charts today. All right, so C is a critical number. And we would also say that the point C comma f of C is a critical point. I'll be abbreviating critical point with CP, right? And again, what makes this a critical point is that here the function is defined, however, its derivative is not. All right, it is not differentiable at that point. Another way that this may look like, well, let's see. If we had something like this, right? Here, I'm able to draw that tangent line. So because I'm able to draw that tangent line like that, that means that this is differentiable, right? So a few things about this. In here, in this scenario, f of C is defined. Good, right? So that means that this value point, this point there, C is in the domain of the function. In here, f prime of C equals 0. How come? Remember that f prime represents the derivative, right? But in practice, we were talking about it being the slope of the tangent line, right? So the slope of the tangent line at this point is 0. Oh, well, yes, because it's a horizontal tangent line, right? And we know that the slopes of a horizontal line is 0. So in here, this is also a critical number. C is a critical number. And the point C comma f of C is a critical point. All right. So these are the two kinds of ways that we're going to be looking at critical points. The second case being really far more common through our studies. All right. So now theorem before we get to do some examples. All right. I know we've been doing a lot of definitions, but theorem. All right. So this is for the existence of relative extrema. All right. So if F has a relative min or max at x equals c, then C is a critical value or critical number of F. All right. So what is that really saying there? Well, this is really just enforcing or adding to how to find these points. All right. So essentially, it's saying, well, to find a relative minimum or maximum, what you have to look for is the critical values. All right. So that's exactly what this is telling us. To find the relative min or max, look for the critical values. All right. So let's see what this does. So theorem. Oh, excuse me, that was a theorem. So let's find the extrema of f of x equals x to the fourth minus 8x squared. All right. So what we want to do is find the extrema. And well, how do we do this without actually looking at the graph, right? Because in the graph, if we have the graph, it's very simple. We will look at that. There's that point there. Well, how do we find that? Well, that's what this is about. So, well, from this previous theorem, it said that we needed to look for the critical numbers, right? So let's go ahead and look for critical points. So for critical points, all right. So recall that tells us that either f prime of c is equal to 0 or f prime of c is undefined. All right. So, all right. So let's figure out what f prime of x is. Well, f prime of x would be 4x cubed minus 16x. All right. And this is telling me that the value c will make this derivative equal to 0. So let's solve for that. So 4x cubed minus 16x equals 0. I'm going to factor out 4x out of each of these, and I end up with 4x times x squared minus 4 equals 0. So what I really end up with here is that either 4x equals 0 or x squared minus 4 equals 0. From here I get x equals 0. From here I get x equals plus or minus 2. Move the 4 over and take the radical of both sides. So now, in here, what did we just find? Well, we find these 3 points, or these 3 critical values, 0, positive 2, and negative 2. Right? From 0, I get the point 0, 0. How did I find that out? I plugged that into here. 0, 0. So 0 to the 4th, 0 squared, 0 minus 8 minus 0 is just 0. All right, now let's figure out what happens when I plug in 2. When I plug in 2, 2 squared is 4. 4 times 8 is 32. 2 to the 4th is 16. 16 minus 32 is negative 16. All right, let's plug in negative 2. Negative 2 to the 4th, well, it's a negative value raised to an even power. That's going to be positive. And 2 to the 4th, 16. Negative 2 squared, 4. 16 minus 32, right? 8 times 4, 32. Negative 16. So there we go. We just found the critical point, the critical points. All right. We found where they are. Now let's look at the visual to this so you can see how this makes sense. That original function, x to the 4th minus 8x squared, it looks as follows. Something like that, right? Let's make that look a little bit better. There we go. So in here, we have critical points here, here, and here, right? Because those are the relative mins and max. And, well, that's exactly what these values are. This point 0, 0, this point negative 2, negative 16, and 2, comma, negative 16. Those are the relative mins and max of this interval. Excuse me, of the function. All right. Next one. Let's say that I said, so that was A. Let's say that I said find the critical points of f of x equals sine square of x plus cosine of x on the interval, open interval, from 0 to 2 pi. All right. Okay. So again, we're looking for critical points. So because we're looking for critical points, that means we're looking for relative extrema. So take the derivative. So critical points, and again, that's where f prime of c equals 0, or it's undefined. And, well, let's figure out what f prime of c is. Well, f prime of x would be, take the derivative, so the derivative of sine squared is 2 sine x cosine x plus the derivative of cosine. Well, the derivative of cosine is negative sine x, so minus sine x, right? And at this point, well, we want to figure out where this is equal to 0, right? And let's go ahead and solve that. So I see that they both have sine, so I'm going to factor out a sine of x, and we're left with a 2 cosine of x minus 1. So I get either sine of x is 0 or cosine of x is equal to 1/2, right? And from here, well, this gives me the point, well, I'm figuring out where sine is 0. That happens in this interval between 0 and 2 pi, not including 0 and not including 2 pi. It only happens at pi. In here, where is cosine x equals to 1/2? Well, in this interval between 0 and 2 pi, if you recall from the unit circle, it happens at pi over 3 as well as at 5 pi over 3, right? And as far as what are the points that these give us? Well, if I plug in pi into here and here, right, because I need to figure out the actual coordinate, and coordinates go back to the original function, f of x there. So in here, this is going to be, well, plug in 0, sine of 0, 0. I don't know why I'm plugging in 0. I'm plugging in pi. Plug in pi. Sine of pi, 0. 0 squared, 0. Cosine of pi, negative 1. So I end up with pi, comma, negative 1, right? 0 minus 1, negative 1. Plug in pi over 3. Well, what do I get? Sine of pi over 3. That's, well, let me actually do it on the side here. It might be a little harder to keep track of. Sine squared of pi over 3. So this is f of pi over 3. Sine squared of pi over 3 plus cosine of pi over 3. Sine of pi over 3 is going to be radical 3 over 2, right? And then we're squaring that. And then cosine of pi over 3 is 1/2. Now, what does that give me? That gives me 3/4 plus, I'm going to write it as 2/4, which is 5/4. So there it is, 5/4. All right. For sine of, so for f of 5 pi over 3, we get, well, pretty much the same process here, except, well, I'll write it. So we end up with sine square of 5 pi over 3 plus cosine of 5 pi over 3, which then gives us this negative radical 3 over 2 squared plus cosine of 5 pi over 3 is still 1/2. But this negative squared now makes it back down to 3/4, sorry. And then 1/2 is 2/4. That's awful. Let's just rewrite that. And overall here we get 5/4 again. So we also get 5 pi over 3, comma 5/4. All right. So those would be the critical points, right? And again, those are relative max and mins. Now let's see what the graph looks like for this function, right? And in that interval, well, I'll draw it overall, and I'll draw the stuff that's out of the interval dotted, right? Just so you see what it's supposed to look like. All right. Maybe I won't draw it dotted. That might be too much. All right, so here we go. Something like that. And it goes. It keeps repeating. But in here, this is the region that we're concerned about in blue. And these points are here, here, and here, where this first one is at pi over 3, comma 5/4. This next one is at pi, comma -1. And this last one is at 5 pi over 3, comma 5/4. All right. And again, this was the region that we were concerned with. All right. All right. So that was finding some critical points there. All right. Now, again, in general, the process is the same for finding the critical points. Is you take the derivative, set it equal to 0. All right. But now let's talk a little bit about finding the absolute extrema. All right. Because we also spoke about the absolute extrema. So I think I'm at example D, right? No, C, not D. So example C. So in here, let's say, so find the absolute extrema of h of x equals x over x plus 3 on the interval from -1 to 6. And notice here I'm doing a closed interval, all right? I'm doing a closed interval. Unlike in the previous examples, here I give you an open interval, right? Because it's not having the or equal to on either side. That means that's what makes it open. And here I didn't even give you an interval because it's implied that I'm talking about throughout its entire domain. So its entire domain is all real numbers. So in here, in C, I'm explicitly saying which interval we care about. All right. So that only in general happens when we're looking for absolute extrema. So the absolute extrema, if you recall, what I mentioned earlier was that the absolute extrema can happen at the endpoints or at a critical point. All right. I think I said it. I phrased it differently. I think I said at the endpoints or at the relative extrema, right? Which again would be the critical points. So let's figure out what happens at the endpoints here. So endpoints. So if I look at this, at these values, so let's plug in h of negative. So let's plug in -1 into h. So I have -1 over -1 plus 3, which gives me -1/2. Okay. So that's a contender to be an absolute extrema, right? Because it can happen at the endpoints. The next contender, h of 6, the other endpoint. So we have 6 over 6 plus 3. That's 6/9, which is 2/3. So far, those are the only contenders, right? The other contenders that we said might exist would be on the critical points. So let's see what happens here. Let's find critical points. And again, the critical points are where f prime of c equals 0 or is undefined. All right. So in this case, my function is called h. So I'll rename that. Okay. So let's figure out what the derivative is. So I need h prime of x. Well, let's recall what the function was. X over x plus 3. So that tells me that I need to use the quotient rule, right? The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. All right. Simplifying this a little bit, I get, well, let's get rid of all those extra parentheses and ones. And now x minus x goes away, so I end up with just 3 over x plus 3 squared. All right. So that's my derivative. Next thing here, well, in here I said that it happens where it is undefined or it is the derivative is equal to 0. So let's figure out where the derivative is equal to 0. So h prime of c equaling to 0. So we have 3 over x plus 3 squared equaling to 0. Now here I have a fraction equaling 0. The only possible way for a fraction to equal 0 is if the numerator itself is equal to 0. But that doesn't make sense in this case, right? There's no value that would make 3 be 0. So what we have here is there's no critical points of this kind. Now let's figure out the undefined part. So I have 3 over x plus 3 squared. And now in here, what would make this undefined? Well, what would make this undefined is if we somehow broke the rules of math. And what would break the rules of math here? Well, if the denominator is 0. So that would give us x plus 3 squared being equal to 0. If we solve this, that tells us that x would be equal to negative 3. However, let's look at this negative 3. If you think about, well, actually right away in here, negative 3 is not in the region that we care about. I said we wanted it from negative 1 to 6. So it's not even, so we don't even care about it for this specific problem. But even if I didn't give you that, if I plugged it into here, if you'll note here, the domain of this function overall, if I was not caring about this, is that x cannot be equal to negative 3, right? So in here, so why do I care about that in there? Well, that would tell me that there's no value, that when I plug in negative 3 into here, I get undefined, right? And that already fails the definition for a critical point, because a critical point needed to be defined, the function needed to be defined at that c value, in this case that c value being negative 3, right? So in here, this is also irrelevant. So these two together, we're told that there's no critical point on the interval that we were looking at. All right, so let's see what we just found here then. Since we got no contenders out of the critical points, there are only two contenders for the max and minimums. Well, since these are the only two contenders, well, this right here would be a minimum, and this one right here would be a maximum, right? Because this is the smallest y value, this is the biggest y value, right? Again, the endpoints only happen at 3 spots. The absolute max and min in a closed interval only happen at three spots: the left endpoint, the right endpoint, or a critical point. So the only possible things there are these two. So let's look at a visual here, so you see what this looks like, what this specific function looks like. All right. So in the interval that we were discussing, from negative 1 to 6, this function looks something like this. All right. it is a curve, right? Where this biggest value here happens at 2/3, and this smallest value here happens at what was it? Negative 1/2. All right, and here clearly we can see that in this curve there's no relative max and mins, right? So these were the only possible two contenders. This is the absolute max on the interval, and this is the absolute min on the interval, and there's no relative max or min. All right, so now let's look at a different scenario. All right, example D. Find the absolute extrema of f of x equals ln of x over x on the interval from 1 to 4. All right, so again here, just like in the previous example, we're looking for the absolute extrema of in that interval, right? So because we're looking for the absolute extrema, well, there's three spots where it can happen, right? There's three contenders: the left endpoint, the right endpoint, or the critical point. So let's first figure out what happens at the left endpoint. So endpoints. So the left endpoint is at 1, so f of 1 would be ln of 1 over 1. All right, well, ln of 1 over 1, ln of 1 is 0, so I guess 0 over 1, which is just 0. Okay, the right endpoint, f of 4, ln of 4 over 4, which, well, let's reduce this. 4 is the same thing as saying 2 squared, and we have that over 4, which using rules of logs, I have 2 ln of 2 over 4, which becomes ln of 2 over 2. All right. If you plug that into the calculator, you'll see it's approximately 0.3465. All right. So we've got two contenders so far, right? The left endpoint and the right endpoint. And I said the third contender would be any critical point. So let's figure out where the critical points happen. So critical points. And we're going to look at, again, remember that's where f prime of c equals 0 or undefined, right? But it must be, but f of c must exist. All right, so now let's see, f prime of x. What am I going to do? Well, notice here that I have a quotient, right? I have this fraction, so it's a quotient, so I'm going to use the quotient rule. So the derivative of the top, 1 over x, times the bottom, x, minus the derivative of the bottom, 1 times the top, ln of x, all over the bottom squared. All over the bottom squared. So 1 over x times x, that just becomes 1 minus ln of x, and this over 2, right? And now the next thing is, well, where would this be 0 or undefined? All right. Well, in here we're gonna say, well, let's look at where f prime of c is equal to 0. So I'm gonna have 1 minus ln of x over 2 equal to 0. Multiply by 2, subtract 1. Well, actually, let's do this. Multiply by 2. 1 is 1 minus ln of x is equal to 0. Move the ln of x to the other side. I end up with 1 is equal to ln of x. To get rid of the ln, we exponentiate with base e. So I have e to the 1 is equal to just x. So, well, in here we just found that x equals e, right? E to the 1 is just e. All right, so we've got a critical point here, based, a critical value based on f prime of x being 0. And now what would that be? Well, if I plug in e into the original function, right, to figure out the actual point, ln of e, 1 over e. So this gives me the point E comma 1 over E. All right, now, well, what's 1 over E? 1 over E is approximately, so let's say this, 1 over E is approximately 0.3678, all right, which if you notice, well, first of all, that's a 3, there we go, 3678, which notice is a bigger value than this 3465. So this right here would now be the relative max, or actually the absolute max. It would also be a relative max. It's a relative max because we got it from being a critical point. It's an absolute max because it's bigger than the other point, than all the other points that we found here. This one right here would be the absolute min. But notice that we don't have any relative min, all right? We don't have any relative minimums here. So the question though was about the absolutes. So we have the absolute max, we just said that was at E comma 1 over E, and the absolute min was at 1 comma 0. Right, that's right here, 1 comma 0. And let's look at what this function, or the visual for this function, so you can see this, what it looks like, what we just found. So this function overall kind of looks like this. Right, where here that value there is 1, here that's 4, this point is at 4 comma ln of 4 over 4, this point right here is at 1 over E, right? Sorry, this point right here is at E comma 1 over E, right? The x value is E, so E comma 1 over E. And I mean, this is an exaggerated graph, right? Because I mean, this point right here is 0.3. This is 0. Sorry, this one was 0.34, right? 3465, the bottom one, and this one was 3678. So this is not drawn to scale, but the idea still stands. All right, and as far as this is concerned, again, this value is this in the interval between 1 and 4, because that's what this problem asked about. In that interval, the absolute max is this value. The relative max, also this value. Absolute min, this value. Relative min, none. There's no relative min here. All right, and this value over here is nothing, but it was a contender for an absolute max or min. All right, so that is how to find absolutes and relative max and mins. And that is the end of 4.1.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.